Okay, welcome everybody to Saturday Surprise. Saturday Surprise. A couple of you asked some questions about, I gotta make sure I have the right color here. A couple of you asked some questions about homeworks number 50 and 52. And I realized that, I never really taught you guys how to use Excel. Okay? And I kind of meant to do that during lab, but of course we're not having lab. So so we get a Saturday surprise for you guys, a little bit of extra content, more than you paid for. Yeah, that's how it goes around here. All right, so I'm gonna give you guys a little bit of a boost on number 50 and number 52. I'm gonna show you how to use Excel to figure out what the order of these experimentally determined rates are. Okay, and as you can hear, we got some sweet elevator music playing in the background, just to set the jive, set the tone for the Saturday surprise. All right. Okay. So number 50 is essentially giving us the concentration of N2O5 over time. Okay. And as you can see, N2O5 in this example is a reactant, and so it's slowly going away. Now the question is, how fast is it going away, and what is the rate of its disappearance? If we can figure out the rate of its disappearance, we can figure out which integrated rate law to use, and therefore predict exactly how much N2O5 is present at 250 seconds. Okay, so the goal is to figure out if it's 0th, 1st, or 2nd order integrated rate law. Okay, so let's write out those three. So 0th order. The integrated rate law looks like A as a function of time is equal to negative kt plus A at time 0. So here we have y is equal to mx plus b. Okay, so that's a straight line. If we plot A sub t, or the concentration of A at time t versus time. Okay, that should give us a straight line. Next, first order. This looks like natural log of A sub t is equal to negative kt plus the natural log of A sub naught. Okay, so in this case, y is ln of A sub t, negative k is m, t is x, and ln of A naught is b. Okay, so if we plot the natural log of A sub t versus t, it should be a straight line if it's first order. Okay, next, second order. In the case of second order, the integrated rate law looks something like this. 1 over A sub t is equal to positive kt plus 1 over A naught. Okay, in this case it's y, mx, and b. So if we plot 1 over A sub t versus t, we should get a straight line if it's a second order rate law. Okay, so the things that I want to focus on here is I want to take 1 over the concentration of N2O5 at time t. I want to take the natural log of the concentration of N2O5 at time t, and I want to look at just the concentration of N2O5 at time t. All of these versus t. And if I do plots of all of these, whichever one is a linear trend, it represents the order of the reaction. Okay, so let's switch over to Excel. All right, I already have the data input here. This is exactly the same data that's given in the textbook. Okay, so we have time here in seconds, and we have N2O5 concentration here in molarity. Now I need to take I need 3 different types of data here, so I'm going to do them over here. Make 3 rows here. So this row is going to be just N2O5. Oops, whoa, don't know what happened there. That's a weak oxygen. Okay, so that's the first, N2O5. This is A sub T. So let's draw out, or let's write out the expression that we just had for the integrated rate law, just to be explicitly clear. This next one should be ln of A sub T. Okay, and this one for the second order should be 1 over A sub T. Okay, so we can just compute those three here. In this case, it would be the natural log of N2O5 concentration at time t. And in this case, it would be 1 over the concentration of N2O5 at time t. And these aren't capitalized, which we can't deal with that. That was a 0. Okay, so this is what we need to put in these squares down here. So I'm just going to go ahead and make them outlined to make it easier to see. Okay, so in this box here, we're going to put in what's called a function. Okay, to put in a function in Excel, all you have to do is hit the equal sign, and now it's in function mode. Next, I want to type in exactly what I want to show up within this column. And since this is just the concentration of N2O5, all I have to do is select the cell using my arrow keys. Okay, so I just pushed over twice with my arrow key, and now it's in C3, and I hit enter. Okay, now it's showing the exact same value that's in this cell. And I can select this cell, and see that little green square down at the bottom of the cell? If I grab that with the cross cursor and I drag it all the way down, it's going to copy that function and iterate it one cell all the way down. So you can see up here in my function bar, you can see what exactly is written within that cell. For example, here it's equals C3. That's the one that I put in. And then as I dragged it down in Excel is smart enough to know that I want it to iterate to the next level here, okay? And then on and on and on, okay? Okay, so now I have AT, or N2O5 as a function of time. That's the 0th order. Next, I want to compute the natural log of the concentration. And all you do here is simply type out the function for the natural log. You can see it brings up this little function icon here, and it tells you what the function does. There's many different functions within Excel. If you're ever curious, you can look them up online. Okay, or you can hit this little button here, and it pulls up a list of all of the functions that you can use. Okay, but we know the natural log is given by ln, so we can just plug that in. And now we need to put in the value for the cell that we want to compute the natural log of. Okay. Now, we can use the arrow keys again to move over, or we can simply type in the cell that we want it to compute the natural log of. So if you look up top here, this is column C and row 3. So this cell right here is cell C3. So if I just type C3 in here, it knows that, and it selects the cell. And then I close the parentheses, hit enter, and it's 0. Good, which is exactly what it should be for 1. Now we can do the same thing we did before. Drag this little green square all the way down, and it copies that exact formula, except it iterates down to C4, C5, see I'm looking up here, C6, C7, etc. So it's calculating the natural log of the value that's in this cell here. Whoops. Okay. Next, I want to compute 1 over the concentration. So this is simple. You just type 1 divided by C3, enter, and you do the same thing all the way down, just like before. So now I have all three: 0th order, 1st order, and 2nd order. Okay, I want to plot all of these as a function of time. Okay. And the way that I can do that is if I select, let's do 0th order first. So if I select all of these, just click in the one cell and then drag your cursor all the way down and then release. Okay, that's 1. Actually, sorry, I have to do x first. So I want the time to be the x coordinate. So whatever you select first is going to be the x coordinate. So click at the top, drag all the way down. I've selected my x column. Now I want to select my y. And to do 2 columns at once, you have to press and hold down the control key. So I'll press the control key, hold it down. Now I can select a second row, and this will be represented by, this will represent the y value. Okay, so this is the x coordinate and this is the y coordinate. Now if I go up here to the top row, and I go to the insert ribbon, okay, it brings up all this really amazing stuff. And right here in this charts section, there's this little button down here that looks like a bunch of dots. Okay, this is called a scatter plot, which is what we want to insert. Now the first option here is just an XY scatter, and that's exactly what we want to insert. Okay, so we'll insert that. We'll move it over here, and then we'll rename it right away. Whoa. We'll rename this 0th order. Okay, and within this graph, we can come over here to the plus key, and we can add in axis titles. Okay, and when we have the axis titles, we want to go ahead and put in exactly, oh my gosh, exactly what is on each of these axes. This axis is just the straight concentration, so I'm going to put that there. And this axis is time in seconds. Okay, so that's 0th order. Now, does this look like a straight line to you? It does not look like a straight line to me. So already, right away, I can say that this is not a 0th order reaction. Okay, let's look at 1st order. So click out of that, and then I select my x-axis again, and my y's. This time going from the center column. Go to the insert, scatter plot. Ooh, this is looking promising. Okay, that's a straight line for sure. Oh gosh, why does it keep doing it? Okay, let's call this 1st order. And then I want to have the axes titles present, so I know exactly what I'm dealing with here. So this is the natural log of N2O05. And this down here is time in seconds. Okay, so this looks like a straight line, but let's go ahead and do 2nd order just to double check. Okay, so that looks like the perfect candidate. Let's do 2nd order though. Click outside, select the X, then select the Y, go to insert, scatter plot. Yeah, so you see here this is quite curved again, so it's not a straight line. So I would say, so this is 2nd order. Dude, this music, it's awesome. I love elevator music. I don't know why. It's just one of those things. Every time I'm in an elevator and it's playing actual elevator music like this, it just makes me so happy. It's one of those things in life that people always look at me kind of strangely and like, are you okay? But yeah, it's just one of those things. I really love elevator music. Okay, yeah, so what we have here, we have 0th order, 1st order, and 2nd order. And 0th order and 1st and 2nd order are clearly curved. They're not straight lines, okay? And what we saw from previously is that if we have any of these, right? If any of these are correct, it will give us a straight line that has the form y equals mx plus b, okay? So This is not straight, this is not straight, but this is straight. So that tells us that this whole reaction is represented by first order kinetics. Okay, so right here, this is represented by first order kinetics. And now, so I'm going to delete these two because they're useless. We know that it's first order. Great. Now what we can do is we can fit this to a linear function, and we can back out this linear equation here. So we can back out m, and we can back out b, right? Just by fitting this with a straight line. Okay. So we select the data points within the graph so that they all look kind of like that. And then we choose any of these data points and we right click on it. And we come down to this little thing here. It says add a trend line. Click add trend line. And the first option here is linear. We want a linear we want a linear function. Then we have to come down here and check some of these boxes. Okay. We want to display the equation on the chart, and we want to display the r squared value on the chart. Now, the intercept, you could set it to 0, but we do not want to do this, okay? So if yours is already checked, set to intercept to 0, uncheck that because we don't want that to be the case, okay? Our intercept will probably be very close to 0 in this case, but... Okay, so the intercept is not set to 0. Everything, we're displaying the equation on chart, and we're displaying the r squared value on the chart. Now we can just X out of this, and you can see that it's fitted with this line here, this dashed line, and it gives us this equation. So let's make this a little bit larger so we can see. Okay, so we have a little bit more data there. And yeah, our equation is giving us negative 0.0078 for the slope and negative 0.0002 for the b value. Okay, so let's write those. Actually, you know what? I can probably just copy this. Oh, by the way, before I go, this r square value represents how well the data fits a straight line. And as you can see, it's a 1. And the closer this value gets to 1, that means that the better the fit of the straight line is to the data. Okay, so usually it's it's a little bit less than 1, like 0.998 or something like that, or even down to 0.8. But in this case, it's exactly 1, which means that this is an excellent fit to a straight line. Typically, in an experiment, you won't get an r squared value of 1, but this is just telling you, yeah, this is exactly a straight line. Okay, that's all the r squared value means. Yeah, so let's copy that and move back over here. Let's paste. Okay, good. Wait, can I make that bigger? Yes, I can. Cool. Let's make it 20. Okay, so I have our equation here. This is oops, I'm still red. Not a big deal, but I think it's easier to see the black. Okay, so from this we have m equal to negative 0.0078 and b equal to negative 0.0002. Okay, now let's go back up to our first order guy. Okay, we found that it's first order. Okay, so we need to use this equation here. So ln of at is equal to negative kt plus natural log of a naught. Did I get that right? Yes, I did. Excellent. Okay, so we have m and we have b. So m is equal to negative k. So that means that k is equal to negative m is equal to 0.0078. Okay, and this is first order, so the oh man, oh yeah, the this is first order, so it would be per second is the correct unit there. okay, per second. And then b is equal to the natural log of a naught, a naught, and that is equal to negative 0.0002, okay? And if we take e raised to the negative 0.0002, oh wait, no, that's not gonna work. Oh yeah, sorry, a naught is equal to e raised to the negative 0.0002. E raised to a really, really tiny number basically is going to be approximately 1, which is great because that's exactly where we started with. Our initial concentration was around 1, so B getting back close to that makes a lot of sense. We can go ahead and actually plug these numbers back in to this equation here and then use it to predict the concentration at 250 seconds. Okay, so at 250 seconds, T is equal to 250 seconds. So we have natural log of a T is equal to negative 0.0078 per second multiplied by 250 seconds plus, actually negative minus 0.0002. Okay, so I'm taking this guy and this guy from the fit, and I'm plugging them directly into the formula, and I'm solving for the natural log of A concentration at time t. Okay, so I end up with some numbers here. Let's see, natural log of A sub t is equal to 0.0078 times 250 seconds. Let me get my calculator real quick. .0078 times 250 is equal to 1.95. So that's negative 1.95. Seconds cancel out. Minus 0.0002 is equal to negative 1.95. It's not enough to really matter. Okay, so this is natural log of A at time t. Now to solve for A at time t, I need to take the exponent of both sides. The exponent gets rid of this natural log here. So I end up with A sub t is equal to e to the negative 1.95 is equal to, let's see, .142. Okay. And this is a concentration, so that's in molar. Okay, let's look at the list of concentrations that we had. So we were given up to 200 seconds. At 250, it would make sense that this would drop down, which is exactly what we see here. So this concentration makes sense with what we see. So right away, I'm going to say that this is probably right. And the concentration at T equals 250 seconds is, well, actually, you know what? Let's make this explicit. Let's say concentration of N2O5 at 250 seconds is equal to 0.142 molar. Okay? So that's how you use Excel to figure out which one works. Basically, just plot them all, and whichever one has a straight line is the correct integrated rate law. All right. I hope that helped. Hope you guys learned something here, and I hope you guys have a wonderful Saturday. Yeah, keep it up. See you guys Monday. Don't feel free to email, or no. Feel free to email me if you have any questions. Yeah, see you guys later.